In this lecture video, we move into the next module, which is on the Randomized Complete Block Design. We're going to see how to use the Randomized Complete Block Design to deal with an extraneous source of variation. Now, to do this, let's first take a step back and consider where we've been. We've been looking at the completely randomized design, which is applicable when we have enough experimental material that is homogeneous to accommodate all of the treatments and all of the replications that we want in an experiment. So in this graphic here, this blue square represents the experimental material that is available for the experiment, and because it's all the same color, that is a representation of the homogeneity of that experimental material. Now suppose that we have 5 treatments that we want to incorporate in the experiment, and that we have enough of this homogeneous experimental material for each treatment to be replicated 5 times. So we can partition this experimental material into 25 experimental units, as I've done here, and then we can attach to each experimental unit a label that identifies which unit it is. Now let's think about the randomization process for a completely randomized design. Remember that in a completely randomized design, treatments are randomly assigned to experimental units completely at random. There's no restriction on the randomization. And so this can be accomplished in a variety of ways, which we've discussed in previous lecture videos. You could use a process that is as simple as pulling slips of paper out of a hat, or you could use a program, a statistical program, or some other type of program that generates pseudo-random numbers to perform the randomization. Now here on the screen I have on the left side some SAS code, a SAS program, to perform the randomization for a completely randomized design for this situation. On the right-hand side, I've listed out the randomization schedule. Again, we have 5 treatments shown here in the first column, and we want to have 5 reps for each of the 5 treatments. And so we're going to utilize all 25 of our experimental units. I have 25 rows here in my table. And so the program that I've got there on the left, using the random number seed that I've got listed there, creates the following randomization. And so I've got the experimental unit numbers in the second column showing us which experimental units each of the treatments is assigned to. And so, for example, we see that treatment 1 is assigned to experimental unit 3, experimental unit 14, experimental unit 18, experimental unit 21, and experimental unit 24. Treatment 2 is assigned to the following experimental units: 4, 7, 8, 11, and 16. Treatment 3 is assigned to experimental units 1, 2, 10, 19, and 22. Treatment 4 is assigned to experimental units 6, 13, 15, 20, and 23. And then finally, treatment 5 is randomly assigned to experimental units 5, 9, 12, 17, and 25. So that is one randomization possible using a completely randomized design. Again, there's no restriction. There's no restriction on the randomization process in terms of restricting which experimental units can get which treatments. It's done completely at random. That's why it's called the completely randomized design. So there is the full design, the full randomization, I'm sorry. And I would just point out that for this particular situation with 5 treatments and 25 experimental units, so that we're having equal replication for all treatments, under the completely randomized design, the number of possible randomization is quite large, 6.23 times 10 to the 14th. So that is the number of possible randomizations. And again, that's obviously a very large number. In fact, that is from sources that I've seen in the past. That number is larger than the number of stars in the Milky Way galaxy. So if you look up in the sky on a clear night and you're only seeing a portion, right, of the Milky Way galaxy. In fact, even if we had no light pollution, the number of stars that you could see would be just a subset, just a portion of the Milky Way galaxy. But the number of possible randomizations for this particular situation far exceeds the number of stars in the Milky Way galaxy. Now here's a picture of the Andromeda galaxy, and they used to think that the Andromeda galaxy was quite a bit larger than the Milky Way galaxy, but in recent years they've changed their minds about that, and they say that the Andromeda galaxy is about the same size as the Milky Way galaxy. And so this is probably very similar to what our galaxy looks like from outside. And so again, the number of randomizations possible for this completely randomized design exceeds the number of stars in this particular galaxy. All right, so that was just kind of an aside. But now let's think about what if we have, what if our experimental material is not homogeneous, right? So it's not that solid, it's not that same color, all right? So here we have a graphic that shows different shades of blue, all right? And so this is a representation of experimental material that is heterogeneous. And in this particular situation, we can think of this as representing a gradient amongst our experimental material. So for example, this could represent a field on an agricultural research station. And so the gradient could represent some kind of a fertility gradient. Maybe the gradient represents the differing soil types as you move from one part of the farm to the other, say north-south. This could represent, for example, continuing with the farm example, maybe it represents moisture levels, right? So you might have different shapes and slopes and so forth on the field, and that could induce different water holding characteristics. So the gradient could represent moisture levels as well. Really, it's really anything that could impact the response measured on the experimental units that we've got in an experiment. But the bottom line is, with this experimental material, it's not homogeneous because the color is not the same. We've got heterogeneous experimental material. Now let's suppose that we have decided to use a completely randomized design, even though we've got this gradient or this heterogeneity in the experimental material. Now, we may decide to use a completely randomized design because we may not be aware of the heterogeneity that exists in the experimental material. That's certainly one possibility. And so, regardless of the reason, let's just suppose that we do have this heterogeneity in our experimental material and that we were to use a completely randomized design for the experiment, and we'll go ahead and use that same randomization that we looked at in the previous situation. And so we've got these treatments randomized completely at random to the 25 experimental units. And you can see here that the response that we would measure on the experimental units is not due just to the different treatment, but it's due to the different characteristics of the underlying experimental material, right? Up here, the experimental material is lighter blue, all right? But down here, the experimental material is darker blue, so representing, heterogeneity in the material. And again, we've got this gradient. And so, for example, if we look at this experimental unit that I am circling here, which has received treatment 2, all right, the impact that we're going to see on the response is going to be influenced not only by treatment 2, but also by the lighter shade of blue that we've seen. On the other hand, this experimental unit down here in the lower left that I'm circling, the impact, the effect on the response of that unit receiving treatment 2 is going to be influenced not only by that particular treatment, but also by the fact that the experimental unit has a darker shade of blue. All right, so perhaps this might be more fertile than this up here, right? So that would have a positive impact, for example, on the response of a crop. All right, and so you can look at the different experimental units and the different treatments that are being applied to those units. And what you can see here is that the response that we are measuring is impacted not only by the treatment that is being applied to the experimental unit, but also by the underlying conditions that exist within each of those experimental units. If I contrast that, let me scroll back up here to the previous situation where we had homogeneous experimental units. In this situation, the response that I'm measuring on each of these experimental units is based primarily on the impact of the effect of the treatment that's being applied, right? Because the experimental units are homogeneous, we're really not going to see that much of an impact from differences in experimental units. There will be some again, some random variation, could be measurement error, but it's also going to be due to differences among the experimental units with respect to their characteristics. But the fact that all these experimental units have the same color is being used to represent the fact that there's not that much variation from one experimental unit to another. So that is again contrasted with this situation here, where because the experimental units are more heterogeneous, there is going to be more variability in the response variable that we measure, right? It's not due, the increased variability is not due to the treatments, it's due to the heterogeneity in the underlying experimental material. Now, if we don't account for that underlying heterogeneity in the experimental material, that's going to have deleterious effects on the analysis that we perform. All right, that increased variability, if unaccounted for, is going to end up in the error variation, and that will, in turn, decrease the power of our hypothesis test and decrease the precision of the estimators that we compute. All right, and so we want to find some way to deal with this heterogeneity that exists in the experimental material. Now, in order to use this process that we're going to be describing, we would have to have an understanding of the nature of the heterogeneity in the experimental material. In particular, we would have to understand, for example, that there does exist a gradient and that it exists in this particular direction. So we can't use blocking, which is what we're going to be looking at. We can't use blocking if we don't understand the nature of the heterogeneity. Now, if we don't have information a priori about the nature of the heterogeneity, then there's at least one other technique that one could use. But what we're focusing on here is what to do if we do understand, at least to some extent, that number one, that heterogeneity exists, and number two, the direction in which that heterogeneity exists, and so forth. So let's look at how we can deal with this by using blocking in the presence of a gradient. And so because the gradient is running, let's call this from in the north-south direction, because that's the direction of the gradient, what we would do to deal with this is to set up our blocks that are oriented perpendicularly to that gradient. All right, and so with the way we've got this set up, we've got fairly long, skinny blocks that are horizontal. Okay, that's perpendicular to the vertical direction of the gradient. And then notice that the experimental material is fairly homogeneous within each of these blocks. So what I've done is I've created 5 blocks, and I've constructed them in such a way that the material within each block is fairly homogeneous. In terms of color, within a block, it tends to have the same shade of blue. There are slight variations within a block, but the shade of blue within a block is much more similar than the difference in shades between blocks. So that is why that's the goal. We want to make that experimental material as homogeneous as possible within a block. And so that's why when we set up our blocks, when we create the blocks are oriented perpendicular to the gradient, all right? And the different blocks run up, along that gradient. Now, what we can do is within each of the blocks, create an experimental unit, partition out that block, and so that we have the experimental units that we require. In this case, we have, remember, 5 treatments. And so the assumption here in this diagram is that each block is large enough to accommodate 5 experimental units, 1 experimental unit for each of the 5 treatments that we want to include in the experiment. So what I've done is partition out each block so that I've got 5 experimental units, and I've numbered them within each block 1 through 5. That's really not necessary. We could label them 1 through 25 if we wanted to, but I've done this just for convenience. And then what we can do now, since we have constructed the blocks, we've constructed them in such a way that the experimental material within the blocks is fairly homogeneous. Okay? Then we can perform a randomized complete block design. And so to do that, we would then perform a randomization that is consistent with the randomized complete block design. And so remember, to do that, what we do is we randomly assign each treatment to 1 experimental unit within each block. And so we've got, in this case, we would have 5 separate randomizations. When we randomize for a randomized complete block design, the randomizations have to be separate for each block. And so we would start off with block 1, and we would randomly assign each of the 5 treatments to exactly 1 of the experimental units within that block. Then we would move to block 2, perform a separate randomization, randomly assigning each of the 5 treatments to each of the 5 experimental units within block 2. And then we would do that for blocks 3, 4, and 5 separately as well. Now, again, you can do that as simply as pulling slips of paper out of a hat, or you can use computer software. So let's see how we might do that. So here on the right-hand side of the slide, I have a table. I listed my blocks, 1 through 5. And then within each block, I have 5 experimental units. So the experimental unit number is listed in that second column. And then what I'm going to do is, to each experimental unit within each block, I'm going to randomly assign each of the 5, or exactly 1 of the 5 treatments. All right, and so again, we're doing this separately for each of the blocks. Now, to implement this, I'm going to use a SAS program again. All right, and so this is a different SAS program that will perform this kind of a randomization for a randomized complete block design. All right, and so let me advance the slide here. Okay, so here is what this randomization would look like. And so you can see the treatment numbers that have been randomly assigned to the experimental units separately within each block. And so starting off with block number 1, we see here that this particular randomization assigned treatment 3 to block 1, or I'm sorry, to experimental unit 1 within block 1, treatment 2 to the second experimental unit, treatment 1 to the third experimental unit, treatment 4 to the fourth experimental unit, and treatment 5 to the fifth experimental unit. For the second block, we see that the treatments were 5, 2, 1, 4, and 3 to experimental units 1 through 5, respectively. Continuing on with block 3, we see that the procedure assigned treatments 2, 5, 4, 3, and 1 to experimental units 1 through 5, respectively. Block 4, the procedure assigned treatments 1, 5, 3, 2, and 4 to experimental units 1 through 5 respectively. And then finally, for the fifth block, the order of the treatments to experimental units was 3, 4, 2, 5, and 1. All right, so you can see this process where we have randomized two experimental units within a block, within each block separately. All right, and again, that SAS code over to the left has been used to accomplish this. Now, with this possible, with this type of randomization, this randomized complete block randomization, the number of possible randomizations is 2.49 times 10 to the 10th. Now, that is still, that's a large number, but it's not nearly as large as the number of possible randomizations under a completely randomized design. And so, in that sense, when we are randomizing for a randomized complete block design, the number of possible randomization is smaller because we're imposing this restriction that we are randomizing each of the treatments within a block for each block separately. Now, if we were to compare the number of randomizations under the two types of designs, we see that the completely randomized design has over 25,000 times more possible randomizations than does the randomized complete block design. Now, that's not additive. I'm not saying 25 times plus. I'm saying 25,000 times. All right, so it's a much larger number of possible randomizations for the completely randomized design than for the randomized complete block design. So that with that in mind, we see that the randomized complete block design restricts the possible randomizations to those which provide treatment comparisons within blocks, effectively filtering out the block-to-block variability. That's why the randomized block design is effective at dealing with an extraneous source of variability, because instead of making treatment comparisons across what we know to be blocks, where we would be seeing not only differences between treatments, but difference between blocks, what the randomized complete block design does is allows us to make treatment comparisons within blocks. All right, so comparisons among experimental units that are homogeneous. All right, and so we get much more precise estimates of treatment effects than would be possible were we to use a completely randomized design where we're not restricting our attention to comparisons between experimental units that are fairly homogeneous. Whenever we make comparisons of treatment effects across experimental units that exhibit heterogeneity, the differences that we observe are due not only to the treatments but also to the differences in the underlying characteristics of the experimental units. And that is why using a completely randomized design with heterogeneous experimental material is not nearly as efficient, it's not nearly as precise as using a different design, such as a randomized complete block design, that takes into account that heterogeneity and effectively filters that heterogeneity out of our estimates. So that's the end of this particular demo. What we're going to do now is transition into the next set of slides on randomized complete block design so that we can see the mathematical features, the mathematical aspects of the model and how we come up with estimators and how we do the analyses.